Welcome to the channel where we explore the edges of human knowledge. Tonight, we journey into territory where even our brightest minds reach their limits. Science has given us extraordinary gifts: antibiotics, spacecraft, computers. Yet the universe guards countless secrets still. Some mysteries dwell in the quantum realm, others in the vastness between galaxies. Some hide within our own minds, while others lurk in the deepest trenches of our oceans. These unsolved puzzles remind us that knowledge is not a destination, but an endless journey. Every mystery represents a frontier where wonder meets the unknown, where questions outnumber answers. If you find peace in contemplating the incomprehensible, consider subscribing or leaving your thoughts in the comments. Others may find their way here through your words. But tonight, let these mysteries wash over you. Let them carry you gently toward rest. And when you're ready, let's begin. Why reality exists at all? The most fundamental question has no answer. Why is there something rather than nothing? Physics can describe how matter behaves once it exists. Cosmology traces the universe back to its earliest moments. But why there should be a cosmos at all? Why laws exist that permit existence? This remains beyond our grasp. Quantum theory tells us that even empty space seethes with activity. Virtual particles flash in and out of existence continuously. Some physicists propose that the universe emerged from this quantum foam, that nothingness itself is unstable. Others suggest our cosmos is merely one bubble in an infinite froth of universes, each with different properties. Yet this only pushes the mystery deeper. If a multiverse exists, why should it? Why should there be laws that allow anything to be? Philosophers sometimes argue that existence is the default state, that non-existence is actually impossible. But we cannot test such ideas. No instrument can measure why being triumphs over void. Every atom, every force, every moment of time rests on a foundation we cannot explain. The fact that reality is here at all remains the deepest enigma we face. What ignited the beginning? Nearly 14 billion years ago, the universe burst into being. We call this moment the Big Bang. But what actually triggered it? That question has no answer. Scientists have reconstructed the universe's history from fractions of a second after the beginning. In those earliest moments, space may have undergone rapid expansion called inflation, swelling faster than light itself. But what started inflation? What set it in motion, and what brought it to an end? These remain unknown. Some theories frame the Big Bang as a quantum fluctuation, a tremor in the fabric of reality that spawns space and time. Others imagine it as merely one phase in an eternal cycle, with universes expanding and contracting endlessly. The problem deepens when we consider time itself. If time began with the universe, asking what came before may be meaningless. Our telescopes, Hubble, Planck, James Webb, capture images of the infant cosmos, but none can peer into that first instant. We know the universe had a beginning. We can date it and chart its growth. But the spark that lit the cosmic fire remains hidden in darkness. The one-way arrow of time. Time always flows forward, yet no law requires it. Every moment, the present becomes the past. We remember yesterday, but not tomorrow. A shattered glass never spontaneously reassembles. Heat dissipates from warm objects into cooler surroundings, never the reverse. This is the arrow of time. What makes it strange is that fundamental physics doesn't demand it. At the quantum level, processes can run backward or forward equally well. The equations show no preference. Yet our entire existence depends on time flowing one way only. Scientists often link time's arrow to entropy, the universe's tendency toward disorder. The cosmos began in an extraordinarily ordered state and has been unwinding ever since. But why did it start that way? Why should the universe have begun in such low entropy that time could even have a direction? Some believe the arrow emerges from how information spreads through systems. Others connect it to cosmic expansion. But none of these explanations feel complete. Time's direction is something we inhabit every waking moment. Yet why it flows forward and never backward remains one of physics' most haunting puzzles. The invisible scaffolding. Most of the universe is invisible to us. When astronomers measure galactic rotation, they find something puzzling. Stars at the edges move far too quickly, as though gripped by unseen mass. Logic says these stars should fly off into space. Instead, they remain bound. The conclusion is unavoidable. Most matter in the universe doesn't shine, doesn't absorb light, cannot be seen directly. We call it dark matter. Dark matter neither emits nor reflects electromagnetic radiation. Telescopes cannot spot it. Yet we know it exists because its gravity shapes everything around it. It holds galaxies together, bends light from distant sources, and leaves subtle traces in the cosmic web structure. But what is it? Decades of searching have yielded no answer. Some think it consists of undiscovered particles, WIMPs or axions, exotic particles that barely interact with ordinary matter. Others propose primordial black holes formed in the universe's first moments. Despite enormous effort, we still don't know. Deep underground experiments wait for a dark matter particle to strike an atom. So far, none has. This hidden mass, 5 times more abundant than visible matter, remains one of nature's greatest secrets. The accelerating expansion. In the 1990s, astronomers made an astonishing discovery. The universe isn't just expanding, it's accelerating. Some unknown energy embedded in space itself pushes galaxies apart at increasing speeds. We call it dark energy, though the its name merely acknowledges our ignorance. Dark energy comprises nearly 70% of everything that exists. Yet we don't know what it is. Perhaps it's a property of vacuum itself, a constant energy present in empty space. Or it might be a dynamic field that changes over time. Some theories suggest it reveals a flaw in our understanding of gravity. What makes the mystery unsettling is its implications. The universe's fate depends on this invisible force. If dark energy remains constant, galaxies will drift apart until only emptiness remains. If it strengthens, it could eventually rip apart galaxies, stars, and atoms themselves. We can measure dark energy's effects, but cannot glimpse its nature. It is the unseen hand writing the universe's final chapter. The fine-tuning enigma, the universe seems calibrated for life with unnerving precision. If gravity were slightly stronger, stars would collapse before life could evolve. If it were weaker, galaxies might never coalesce. If electromagnetic forces differed by a hair, atoms couldn't form. The tiniest changes to physics constants would make life impossible. This is the fine-tuning problem. Why should nature's laws have exactly these values? There's no obvious reason for forces to possess the strengths they do. Yet if they differed even marginally, our universe would be sterile. Some argue it's coincidence. Others propose countless universes exist, each with different laws, and we simply inhabit the rare one permitting life, a cosmic lottery. Another idea is that some undiscovered principle forces the constants to take these exact values. When we observe stars, planets, and our own ability to ask these questions, we're reminded that the universe feels improbably suited for existence. Why that should be remains unexplained. the universe's true size. We cannot see beyond a certain horizon. The observable universe stretches about 93 billion light-years across, but we cannot look past that boundary. Light has only had so long to travel since the Big Bang. Beyond lies a realm forever hidden. Does the universe extend infinitely, with no edge at all? If so, space may contain endless galaxies, stars, and perhaps even other Earths. Or is the universe finite but unbounded, like a sphere's surface? In such a cosmos, traveling far enough in one direction might return you to your starting point. Scientists search for clues in the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns might reveal the universe's shape. Evidence suggests the universe is nearly flat, but this doesn't settle whether it's infinite. The true extent and geometry of the cosmos remain beyond our reach. The unobservable expanse. When we gaze into space, we peer into the past. The most distant galaxies visible sent their light over 13 billion years ago. But beyond that lies a region eternally hidden, the unobservable universe. This cosmic horizon isn't a physical wall. It's a limit set by the universe's age and light speed. Beyond it, reality continues, but we can never know what's there. Perhaps it's similar to what we see: galaxies, stars, planets stretching beyond sight. Or perhaps it's radically different, with regions governed by different conditions or even different physical laws. Some inflation theories suggest our observable patch is merely one bubble in a vastly larger reality. If true, most of the universe lies forever beyond measurement. We inhabit a cosmic island. The sky we see is only the smallest fraction of what may exist. The rest is silent and unreachable, a permanent unknown. The multiverse question. Some scientists believe countless universes exist beyond our own, each with different laws, histories, and dimensions. This is the multiverse hypothesis, one of modern science's boldest ideas. The concept arises naturally in certain theories. Inflation may create bubble universes budding off with unique conditions. String theory predicts a vast landscape of possible realities. Our universe might be just one outcome among infinite variations. This could explain fine-tuning. We live in a life-supporting universe because only such universes can contain observers. But there's a problem. If other universes exist beyond our cosmic horizon, we may never observe them. No signal could cross the boundary. This makes the multiverse both fascinating and controversial. It stretches science's definition by proposing something potentially untestable. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, remains one of physics' most intriguing mysteries. The quantum realm. Einstein showed us that space and time are not rigid backdrops, but flexible and dynamic. They bend, curve, and stretch. But at the deepest level, what is this fabric made of? At the smaller scales, relativity and quantum mechanics clash. Relativity depicts space-time as smooth. Quantum theory suggests everything should be grainy and uncertain. Reconciling these views remains one of science's greatest challenges. Some ideas suggest space-time isn't fundamental at all. Instead, it may emerge from something deeper, perhaps quantum information or entanglement patterns giving rise to geometry. In this picture, space-time is like a surface, and underneath lies a more basic reality we cannot yet see. Others wonder if time itself is real, or if it's an illusion created by deeper processes. If so, our most basic intuition about reality would be wrong. Space and time feel like the stage on which the universe unfolds, yet the stage itself may not be what it seems. What they truly are remains profoundly unanswered. Quantum superposition. A single particle can exist in two places simultaneously, and we don't understand how. Quantum mechanics tells us particles lack definite positions until measured. Instead, they exist in superposition, a probability cloud where many outcomes coexist. An electron can be here and there, passing through both slits, in an experiment simultaneously, interfering with itself like a wave. Only when observed does it choose a location. This isn't mere theory. Experiments have demonstrated superposition with electrons and even with molecules thousands of times larger. Physicists can create delicate states where objects exist in overlapping possibilities. Yet no one truly understands what it means. Does the particle physically exist in multiple places? Or is superposition just reflecting incomplete knowledge? Some interpretations suggest multiple realities split. Others suggest reality is fuzzy until measured. The ability of a single particle to seemingly occupy two places at once remains one of quantum mechanics' strangest, most unsettling mysteries. Quantum entanglement. When two particles become entangled, their properties link in a way that defies distance. Measure one, and you instantly know the other's state, regardless of separation. Einstein called this spooky action at a distance because it seemed to violate the cosmic speed limit. Nothing should move faster than light, yet experiments confirm entanglement is real. Photons, electrons, even small atom groups have been entangled and separated by kilometers. No signal passes between them, but correlations remain perfect. It's as though nature maintains a hidden ledger, ensuring outcomes stay synchronized. What does this mean? Some physicists suggest reality is non-local. The universe is woven more deeply than space and time suggest. Others think entanglement may point to hidden variables we haven't discovered. Still others propose that information itself forms reality's foundation. We use entanglement in quantum computing and secure communication, yet we cannot explain why it works. The universe whispers across distance, and we still don't know how. The measurement problem. One of quantum physics' strangest discoveries is that observation seems to affect reality. In the famous double-slit experiment, particles behave like waves when unobserved, creating interference patterns. But if we measure which slit a particle traverses, the wave-like behavior vanishes. Why should observation change the outcome? One explanation is that the wave function, describing all possible states, collapses into a definite outcome when measured. But what counts as an observer? Is it a measuring device, a human consciousness, or is collapse an illusion hiding deeper laws? Some interpretations say every possibility happens, branching into multiple universes. Others suggest particles only appear definite when information about them becomes irreversible. None of these ideas have been proven. What we know is that the boundary between observer and observed is not as simple as once believed. The universe seems to care whether it's being watched, and no one knows why. The weakness of gravity. Gravity rules the cosmos. It holds planets in orbit, shapes galaxies, governs stellar motion. Yet compared to other forces, it's unbelievably weak. A small refrigerator magnet easily overcomes Earth's entire gravitational pull. Why is this? Electromagnetic, strong nuclear, and weak nuclear forces all operate at tiny scales with enormous power. Gravity, by comparison, is feeble. Physicists have struggled with this hierarchy problem for decades. One possibility is that gravity spreads into hidden dimensions we cannot see, diluting its strength. Another is that gravity's true scale is strong but masked by unknown physics at small distances. Despite centuries of study, we don't understand why gravity is so much weaker than other forces. This imbalance isn't just curious, it's fundamental to the universe's structure. Without it, stars and galaxies couldn't exist. Gravity's weakness is the quiet mystery making the cosmos possible. The theory of everything general relativity describes the large-scale universe with remarkable precision. Quantum mechanics explains the microscopic world with astonishing accuracy. Both theories pass every experimental test we devise, but they don't agree with each other. When we tried describing situations where both matter and gravity are quantum, inside black holes or in the universe's first moments, the equations break down. Infinities pile upon infinities. The frameworks are mathematically incompatible. Physicists have searched for decades for a theory of everything uniting them. Candidates like string theory and loop quantum gravity offer tantalizing possibilities, but no experiment has confirmed them. Without a unifying theory, we cannot truly understand the cosmos's birth or spacetime's nature at the smallest scales. The fact that our two most successful theories describe different realities is one of science's greatest paradoxes. Both work perfectly, yet together they fail. Unsolved: black holes and cosmic phenomena. Black holes are regions where gravity is so intense that nothing, not even light, escapes. As matter falls inward, it's crushed toward the center. Einstein's equations say everything collapses into a single point of infinite density, a singularity. But infinity usually signals that our mathematics has failed. What truly lies at a black hole's heart? Some think the singularity is real, a place where known physics breaks down. Others believe a deeper theory, perhaps quantum gravity, will replace it with something else, a loop of space-time, a finite core, or an entirely new object. The event horizon hides the interior completely from view. For now, the heart of a black hole is sealed away beyond observation and beyond certainty. It remains one of science's most inaccessible mysteries. What singularities are a singularity is where our equations predict infinities, density without limit, curvature without bound, time and space collapsing beyond definition. Black holes contain them. The Big Bang may have begun with one. But what are they really? Are singularities actual features of nature or signs that our theories are incomplete? Many physicists believe they point to relativity's limits. Somewhere beyond, a new theory merging relativity with quantum mechanics must take over. In that theory, infinities might dissolve into something finite and describable. Until then, singularities remain puzzles at physics' edge. They're places where understanding stops and models break. What lies beyond them is hidden, waiting for a deeper theory of reality. The information paradox. When matter falls into a black hole, it seems to disappear forever. But in physics, information, the details about a system's state, is supposed to be preserved. So what happens to information locked inside a black hole? Stephen Hawking showed that black holes can slowly evaporate through radiation. But if they vanish completely, where does the information go? If it's destroyed, quantum mechanics would be violated. If it escapes, then somehow information must leak out through Hawking radiation, a process no one fully understands. This puzzle, the black hole information paradox, has challenged physicists for decades. Some think information is stored on the event horizon itself. Others argue that black holes might connect to other space-time regions, allowing information to escape. Still others think our understanding of quantum mechanics may need revision. The fate of information in black holes is one of physics' most important open questions. It touches not only on black holes, but on reality's deepest foundations. Hawking radiation. In the 1970s, Stephen Hawking made a stunning prediction. Black holes aren't truly black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass over immense timescales. Eventually, they could evaporate entirely. This radiation, now called Hawking radiation, is one of modern physics' most famous predictions, yet we've never observed it. Real black holes are surrounded by hot gas and violent environments that overwhelm the faint trickle of radiation. Detecting it directly may be impossible with current technology. Still, the idea has huge consequences. It ties together quantum theory, relativity, and thermodynamics. It suggests black holes have temperature and that space-time itself is more dynamic than realized. Laboratory experiments have tried creating analogues of Hawking radiation using sound waves and fluids, but these remain indirect hints. Whether Hawking radiation truly exists remains unproven. If it does, it will reshape our understanding of black holes. If it doesn't, something even stranger must be happening at spacetime's edge. Black holes as portals. Black holes push physics to its limits. Inside them, space and time bend in ways we cannot fully describe. Some solutions to Einstein's equations suggest black holes could connect to other space-time regions, tunnels known as wormholes. In theory, entering a black hole might lead elsewhere. But this remains speculation. Wormholes, if they exist, may be unstable. Intense gravity might destroy anything attempting to pass through. Yet the mathematics leaves the possibility open. Some physicists suggest that singularities at black hole centers could mark bridges to new universes with their own space and time. Others think black holes might recycle information, seeding new cosmic regions' birth. For now, we cannot test these ideas. No signal escapes a black hole's interior, so its secrets remain hidden. Still, the idea that black holes may be more than cosmic graves, that they could be gateways to something beyond, is one of the most tantalizing mysteries of all. The first stars, when the universe was young, it was dark and simple. No galaxies, no planets, no complex chemistry. Only clouds of hydrogen and helium drifted in expanding space. At some point, those clouds collapsed to form the first stars, ending the cosmic dark ages and lighting the universe for the first time. But exactly how this happened remains mysterious. These first stars, called population 3 stars, would have been enormous, hundreds of times the sun's mass, burning hot and bright, but living only a few million years before exploding as powerful supernovae. They seeded the cosmos with the first heavier elements, paving the way for later star generations and eventually for life. The problem is we've never seen one. No population 3 star has been observed. They lived and died so quickly, so long ago, that direct evidence is missing. Astronomers look for indirect clues in ancient stars' chemical fingerprints, hoping to find hints of their violent births. The James Webb Space Telescope may finally glimpse their light. But for now, the exact process that sparked the first stars remains one of astronomy's great open questions. Supermassive black holes' rapid growth. At nearly every galaxy's heart lies a supermassive black hole, millions or billions of times the sun's mass. We know how black holes can grow by swallowing gas, stars, and other black holes. But in the early universe, we see black holes that grew far too large, far too fast. Some of these giants already existed less than 1 billion years after the Big Bang. According to our models, there simply wasn't enough time for them to grow so big through ordinary processes. This leaves us with a puzzle. Did they form from enormous primordial cloud collapses, skipping small steps entirely? Did they grow from massive first-generation stars' deaths that collapsed into black holes much larger than expected? Or is there a mechanism we haven't discovered, allowing them to feed and expand at astonishing rates? These ancient black holes challenge our understanding of galaxy evolution. If we can solve their mystery, we may unlock the story of how galaxies themselves came to be. For now, they remain cosmic enigmas, giants that shouldn't exist so soon after the universe began. Spiral galaxy formation. When we imagine galaxies, we often picture elegant spirals, sweeping arms of stars curling outward like cosmic pinwheels. The Milky Way is one. But why should galaxies form such intricate spiral patterns? The answer isn't clear. One idea is that spiral arms are density waves, like traffic jams on a highway. Stars move through them, bunching up as they pass, creating the illusion of permanent arms. Another theory suggests spirals may be shaped by interactions, galaxies tugging on each other with gravity, stirring stars into curving arms. Simulations can recreate spiral structures, but not with perfect consistency. Spirals aren't rare. In fact, they're common. Yet their exact origin and stability remain unsettled. Why some galaxies form beautiful spirals while others become elliptical blobs is still an open question in astrophysics. When we look at the night sky and see the Milky Way stretched across it, we're looking from inside one of these mysteries. Our home galaxy's graceful arms are both familiar and unexplained. Fast radio bursts. In 2007, astronomers detected a powerful radio signal lasting only milliseconds. Since then, hundreds more have been found scattered across the sky. These signals are called fast radio bursts, or FRBs. Each releases as much energy as the sun does in a year, but in the blink of an eye. What causes them? Some FRBs repeat, suggesting they come from ongoing processes like magnetars, highly magnetic neutron stars that can flare with incredible energy. Others appear only once, hinting at catastrophic events such as stellar collapses or compact object mergers. But no explanation fits them all. FRBs travel across billions of light years, distorted and stretched by the matter between galaxies. They may even help us map matter's distribution across the universe. But until we know their source, they remain cosmic puzzles. Every so often, the universe sends us a brief, powerful shout across the void. We can hear it, we can measure it, but we still don't know who or what is speaking. Pulsar precision pulsars are collapsed stellar remnants, neutron stars spinning rapidly, sweeping radiation beams across space like cosmic lighthouses. Discovered in 1967, they were so regular at first that scientists wondered if they might be signals from intelligent life. Today, we know they're natural, but their precision remains astonishing. Some pulsars keep time better than our best atomic clocks, rotating hundreds of times per second without missing a beat. How can an object so extreme, a star crushed into city size, maintain such stability? The answer lies in their incredible density and strong magnetic fields, but details aren't fully understood. Pulsars can also glitch, suddenly changing rotation speed in ways we cannot yet predict. These glitches may come from interactions deep within their superfluid cores, where physics is unlike anything on Earth. Pulsars are laboratories of extreme physics, but they still keep secrets. Their rhythms remain some of the universe's most mysterious and precise signals. Jashursquarachi. Magnetar eruptions. A magnetar is a neutron star with a magnetic field 1,000 times stronger than a normal neutron star's and 1,000,000,000,000 times stronger than Earth's. These magnetic fields twist and snap, releasing sudden violent radiation bursts. Magnetars can unleash more energy in a single second than the Sun produces in 100,000 years. We detect them as intense X-ray and gamma-ray flares. But what exactly triggers these eruptions remains uncertain. Are the bursts caused by starquakes, shifts in the neutron star's crust under magnetic stress? Or are they caused by sudden magnetic field reconfigurations, releasing energy like a snapping cosmic rubber band? Some fast radio bursts have been linked to magnetars, suggesting they might explain at least some of those mysterious signals. But the full picture is still missing. Magnetars are rare, with only a few dozen known, but their power is staggering. They're reminders that the universe contains energy engines we still struggle to comprehend. Ultra-high-energy cosmic rays. Every second, high-energy particles called cosmic rays rain down on Earth from space. Most are protons traveling near light speed. Many come from the Sun or supernovae. But some are so energetic, so powerful, that we have no idea where they originate. The most extreme cosmic rays carry the energy of a fast-pitch baseball packed into a single particle. No known process should be able to accelerate them to such speeds. They may come from supermassive black holes, from active galaxies, or from exotic processes we don't yet understand. These particles crash into Earth's atmosphere, creating showers of secondary particles we can detect on the ground. Observatories like the Pierre Auger Observatory in Argentina track them, trying to trace their paths back to their origins. But magnetic fields in space bend their trajectories, erasing clues. Cosmic rays are constant visitors, yet their most powerful examples remain unexplained. They remind us that somewhere in the universe, nature runs particle accelerators far beyond anything humans can build. The origin of plate tectonics. Earth's surface is alive with motion. Continents drift, mountains rise, oceans open and close, all driven by tectonic plate movement. Without plate tectonics, Earth wouldn't have its landscapes, earthquakes, or volcanoes. Life itself may depend on this restless churning. But why did it begin here and not on other planets? Mars and Venus have no active tectonics. Their crusts are stagnant, locked in place. Somehow, billions of years ago, Earth's crust fractured into giant plates that slide and grind endlessly. Did water act as a lubricant, weakening rock and allowing movement? Did internal heat reach just the right balance between strength and flow? Or was it triggered by ancient impacts that cracked Earth's crust? We don't know. Computer models offer competing answers, but none explain why Earth alone developed this feature. Without plate tectonics, the carbon cycle regulating climate might fail, leaving the planet barren. Plate tectonics is what makes Earth dynamic and habitable. Yet the reason it began and why it's unique in the solar system is still an unsolved puzzle. Truash. Earth's water origin. Water covers most of Earth, filling oceans, rivers, and clouds. It's essential to life. Yet its origin remains one of science's great mysteries. Did water arrive on asteroids and comets delivered during the early solar system's chaos? Some evidence supports this, as many space rocks contain ice. But Earth's water's chemical fingerprints don't always match comets. Another idea is that water was present from the beginning, trapped deep within Earth's mantle, slowly rising to the surface over eons. Perhaps both are true. Some water born here, some brought from space. But the balance is still debated. What we know is that Earth is unusual. Neighboring planets like Venus and Mars are dry, their water lost or locked away. Something about Earth allowed oceans to gather and remain stable. Water is so ordinary that we forget its strangeness. Every drop you drink carries the mystery of its origin. a riddle stretching back to our world's birth. The moon's asymmetry for millennia, humans saw only one moon face. The far side remained hidden until spacecraft revealed it in the 20th century. And what we saw was surprising. The near side, the face we know, is covered with dark Maria, vast plains of cooled lava. The far side looks nothing like it, rugged, mountainous, with almost no Maria at all. Why should the moon's two faces be so different? One idea suggests uneven heating, with Earth's gravity baking one side more intensely. Another proposes an ancient collision reshaped one hemisphere, but not the other. Some theories involve internal dynamics, differences in crust thickness or volcanic activity. But no explanation fits perfectly. The moon should be symmetrical, yet it isn't. Its hidden face carries scars and secrets that defy simple answers. Even now, as spacecraft orbit and landers touch its surface, the far side of the moon keeps its mystery, as though it's still half a stranger to us. Earth's core dynamics. Deep beneath our feet, more than 3,000 kilometers down, lies Earth's core, a ball of molten iron and nickel surrounding a solid inner sphere. Its motion generates Earth's magnetic field, shielding us from solar winds and cosmic radiation. Without it, our atmosphere might be stripped away, leaving Earth barren like Mars. But despite its importance, we don't fully understand how it works. We cannot drill to the core, so we rely on indirect clues, seismic waves, magnetic records, computer models. We know the outer core flows like liquid, and that this motion powers the geodynamo. But why Earth's field sometimes weakens, wobbles, or reverses entirely is still uncertain. Other planets puzzle us further. Mars once had a magnetic field but lost it. Why did Earth keep its protective shield while Mars did not? The beating heart of our planet remains hidden from direct study. We feel its effects every day, in compasses, in auroras, in our very survival, but its inner workings remain mysterious. Magnetic pole reversals. Every so often in Earth's history, the magnetic poles switch places. North becomes south, south becomes north. These reversals are recorded in ancient rocks, showing a flip-flop pattern stretching back millions of years. The last full reversal happened about 780,000 years ago. But why do they happen? Scientists believe turbulence in the liquid outer core, the engine of Earth's magnetic field, sometimes becomes unstable, causing the field to collapse and rebuild in the opposite direction. But the exact trigger is unclear. Sometimes flips are quick, sometimes they take thousands of years, and sometimes the field only weakens without fully reversing. The mystery deepens when we consider the effects. During a reversal, the field weakens, exposing Earth to more radiation from space. Would that disrupt ecosystems? Did past reversals influence evolution? We don't know. All we know is that Earth's magnetic field is not permanent. One day, north will again become south, and the reason why remains hidden in the depths. Ice Age cycles. For millions of years, Earth's climate has swung between ice ages and warmer periods. Vast glaciers have advanced and retreated, carving landscapes and reshaping continents. But why this cycle happens is still debated. Some explanations point to changes in Earth's orbit and tilt, known as Milankovitch cycles, which alter how sunlight reaches the planet. Others suggest volcanic eruptions, shifting ocean currents, or carbon dioxide feedback loops. Perhaps all combine in ways we don't yet fully understand. What is certain is that the rhythm of ice and thaw has shaped human history. Our ancestors migrated, adapted, and survived in glaciers' shadows. Civilizations rose as climates warmed. But the underlying cause, the engine of these repeating freezes remains unclear. Ice ages remind us that Earth's climate is never fixed, but part of a mystery far larger than ourselves. Mass extinction causes 5 times in Earth's history. Life has nearly been wiped out. The dinosaurs' extinction 66 million years ago is the most famous. But even greater catastrophes came before, like the Great Dying 252 million years ago, when most life on Earth vanished. Asteroid impacts, supervolcanoes, climate shifts, and changing oceans have all been proposed as causes. Sometimes the evidence points clearly, as with the asteroid that struck at the Cretaceous end. Other times it's murky, multiple disasters overlapping, creating collapse cascades. Why some species vanish while others survive is equally mysterious. Why did mammals endure the asteroid strike while dinosaurs perished? Why do some extinctions unfold in slow decline while others happen in a geological instant? Mass extinctions remind us of life's fragility, but also of its resilience. Each one cleared the stage for new life forms to rise, but the forces behind them, sudden, devastating, and unpredictable, remain only partly understood. Life's first spark life on Earth began more than 3.5 billion years ago, but the details of its origin remain hidden. Fossil evidence shows microorganisms were already thriving not long after the planet cooled. But how did non-living chemistry cross the threshold into life? One idea is that life began with simple molecules self-organizing into chains capable of storing information, perhaps RNA before DNA. Another is that life emerged from hydrothermal vents' energy-rich environment on the ocean floor, where hot water, minerals, and chemistry combined. Still others propose that life's building blocks arrived from space, carried on comets or meteorites that bombarded young Earth. Each idea has support, but none are proven. Scientists have managed to create amino acids and other basic molecules in laboratory conditions mimicking early Earth. But producing a fully living system remains beyond reach. Life's origin may have been a unique event, or it may be a natural outcome whenever the right conditions exist. Until we uncover clearer evidence, the moment when chemistry first awakened into biology remains one of science's deepest mysteries. Unsolved. Life's birthplace. Our planet offered many possible cradles for the first life. The ocean, covering much of Earth, seems the obvious candidate. Hydrothermal vents, where hot water and minerals pour from the seafloor, provide rich chemistry and constant energy. Many scientists believe life may have begun there, with molecules assembling inside natural mineral compartments. But there's another possibility. Some researchers argue that shallow pools on land, subject to cycles of drying and refilling, could have concentrated molecules and driven the reactions needed to form life's building blocks. Ultraviolet light from the sun, often destructive, could also have powered key steps in these reactions. Both environments seem plausible. Each offers strengths, and each faces challenges. The ocean dilutes molecules, making interaction harder. Land-based pools may have been too unstable. Until stronger evidence emerges, we don't know whether life first stirred in the deep oceans or in the shallow waters of land. The answer remains hidden in the deep past, in rocks and fossils that have long since transformed. The first cell life is defined not just by chemistry, but by organization. Modern cells are intricate structures with membranes separating them from the outside world and molecular machines carrying out countless reactions. But how did the first cell arise from lifeless chemistry? One possibility is that fatty molecules naturally present on early Earth formed bubbles that trapped useful chemistry inside. These primitive membranes could have allowed energy and molecules to flow while protecting fragile RNA or protein chains. Over time, the chemistry inside could have become more complex, eventually becoming self-sustaining. Experiments show that simple membranes can indeed form spontaneously in the right conditions. But how the leap from these primitive compartments to a living cell's complexity occurred is still unknown. This transition from disorderly chemistry to the first organized cell remains one of biology's great mysteries. Until we understand it, we cannot say how life truly began. Why DNA? All life on Earth uses the same molecule to store information: DNA. Its double helix is elegant and universal, carrying instructions for every organism. But why this molecule and why this shape? Chemistry allows for many possible ways to store information. RNA, for instance, is simpler and may have come first. But somewhere in life's early history, DNA took over as the master code. Its stability, its ability to replicate reliably, and its capacity to carry immense amounts of information made it uniquely suited. Yet we don't know why DNA's specific structure, a double helix with precisely paired bases, became the solution all life depends on. Was it inevitable, dictated by chemistry? Or was it an accident, a single successful outcome among many failed alternatives? DNA's universality suggests it may be the best answer nature could find. Still, why life chose this exact path remains an open question, hinting at deep mysteries in the chemistry underpinning existence. Viral origins. Viruses are strange entities. They're not alive in the traditional sense. They cannot reproduce on their own, relying instead on hijacking living cells' machinery. Yet they're not merely inert molecules. They evolve, adapt, and influence life's course on Earth. Where did they come from? Some scientists think viruses are relics of the RNA world, survivors from before fully living cells evolved. Others believe they began as pieces of genetic material that escaped from cells and learned to copy themselves. A third possibility is that they were once living organisms that became stripped down to their simplest form. The truth may be that viruses arose in more than one way, their origins as diverse as life itself. What is clear is that they are ancient. They may even have played a crucial role in complex life's evolution, transferring genes between organisms. Viruses blur the line between life and non-life, and their beginnings remain one of biology's most enduring mysteries. Why some molecules became alive. Early Earth was a chemical playground. Simple molecules formed everywhere, from deep-sea vents to volcanic pools to lightning-struck atmospheres. Among them, some began linking into more complex chains like amino acids and nucleotides. But only a tiny fraction of this chemistry crossed the line into life. Why those molecules and not others? What special property allowed some to organize into self-replicating systems? Was life inevitable once the right ingredients came together? Or was it a rare accident dependent on chance events? Experiments suggest many building blocks of life can form under natural conditions, but creating a self-sustaining, evolving system remains elusive. The leap from chemistry to biology is vast, and we don't yet know how it happened. This uncertainty raises profound questions. If life is inevitable, then the universe may be filled with living worlds. If it was a fluke, then we may be utterly alone. The mystery of why some molecules became alive while others remained inert is one of science's most important unanswered questions. The search for life beyond Earth is the only place we know where life exists. But with billions of stars in our galaxy and billions of galaxies beyond, it seems unlikely we're alone. Still, despite decades of searching, no clear evidence of extraterrestrial life has been found. We've discovered thousands of exoplanets, many in the habitable zone where liquid water could exist. We know that organic molecules are common in space, found on comets, in clouds, and on distant moons. Mars shows signs of a wetter past. Europa and Enceladus hide oceans beneath icy crusts. Conditions for life seem abundant. And yet, the silence persists. We haven't detected signals, nor found microbes on Mars, nor uncovered alien fossils. It's possible life is common but hard to detect, or it may be exceedingly rare, requiring conditions we don't yet understand. Until we find even the simplest alien microbe, the question of whether life exists elsewhere remains unanswered. Alternative biochemistries. All life on Earth is built on the same foundation: carbon, water, DNA, and proteins. But must it be so? Could life exist with a different chemistry entirely? Some scientists think silicon, abundant and capable of forming long chains, could serve as life's backbone. Others imagine organisms using ammonia instead of water, or exotic biochemistries thriving in methane seas like those on Saturn's moon Titan. Still others wonder if plasma, magnetic fields, or information itself could host something like life. We don't yet know the answer. All our definitions of life are shaped by a single example: Earth. It may be that carbon and water are the only real solution. Or it may be that the universe holds living systems stranger than we can imagine. If we discover alien life, it may look nothing like us. It could challenge our very definition of what it means to be alive. Habitable world frequency. Astronomers have discovered thousands of planets orbiting other stars. Many are small and rocky, some in the habitable zone where liquid water might exist. But how many are truly habitable? That's still unknown. Habitability depends on more than distance from a star. Planets need the right atmosphere, magnetic protection, and long-term stability. Some may be scorched by radiation, others frozen by lack of heat. Moons may be habitable too, with oceans beneath icy crusts, but we cannot yet measure them directly. The galaxy may be rich in habitable worlds, or they may be rare jewels. Right now we cannot say. Each discovery brings us closer, but the true frequency of Earth-like conditions remains one of astronomy's great open questions. Butcher. The silence of the universe. For as long as humans have looked at the stars, we've wondered whether life exists beyond Earth. Despite the universe's size, despite the abundance of planets and the chemistry of life scattered across space, we still have no answer. We listen for signals with radio telescopes. We send probes to planets and moons. We analyze distant worlds' atmospheres for life signs. But so far, the silence is complete. It may be that life is common, but intelligent civilizations are rare or short-lived. It may be that life is rare at every level, and we are a singular accident. Or it may be that life is everywhere but hidden from us by distance or difference. The question remains open. Are we a lonely spark in a vast, empty universe, or one voice in a cosmic chorus we have not yet heard? Until we find evidence, the answer to this oldest of questions remains unknown. The mind and consciousness, every thought you have, every memory, every flicker of awareness, seems to arise from the brain. Scientists can measure electrical signals moving across neurons. They can switch awareness off with anesthesia. They can even track brain activity when you focus on a picture or sound. Yet none of this explains why there is an inner experience at all. Why should firing neurons create the feeling of being alive? A brain scan can show activity in the visual cortex when you see a sunset, But it doesn't explain why that experience comes with the glow of red and gold inside your mind. Researchers have ideas that consciousness appears when information spreads across the brain, or when neurons form certain patterns, or even that awareness is a deeper property of the universe itself. But none truly explain the leap from matter to mind. Consciousness is the most ordinary thing. It's what you're experiencing right now. And yet, when we try to explain it, it slips through our fingers. We know it arises from the brain, but the how remains the deepest mystery of all. The purpose of dreams: every night as you sleep, your mind conjures worlds. Some are vivid, filled with people and places you know. Others are strange and fragmented, dissolving as soon as you wake. These are dreams, and though we all experience them, no one truly knows why they happen. Some scientists think dreams are the brain's way of practicing. They may replay memories, strengthening useful connections. Others believe dreams help regulate emotion, allowing you to work through fear, sadness, or conflict in a safe, unreal space. Some say they're simply random firings of a sleeping brain, patched together into stories. What makes dreams more puzzling is their power. A nightmare can wake you in terror, even though you're safe in bed. A good dream can leave you smiling all day. Sometimes dreams even solve problems. Writers, artists, and scientists have all described breakthroughs that came to them in sleep. We know the brain is active while we dream, especially during REM sleep, when the eyes flicker beneath closed lids. But the purpose behind it remains elusive. Dreams are familiar nightly journeys into strange lands, yet their true meaning is still hidden. Time perception. Think of a moment when time seemed to slow to a crawl, a near accident, a sudden fright, an intense experience. Now think of the opposite, a holiday that seemed to vanish in an instant, or hours that disappeared when you were fully absorbed in something you loved. Clock time is steady, but our sense of time is anything but. Why? No one knows for sure. Some believe the brain has an internal clock, and emotions like fear speed it up, while calm states slow it down. Others suggest our brain judges time by the number of events it processes. A moment filled with new details feels longer. A routine one feels shorter. This could explain why childhood summers seemed endless, while adult years slip past more quickly. Novelty stretches our perception. Routine compresses it. But it's only a theory. What we know is that time in the mind is elastic. It stretches, contracts, and sometimes even seems to stand still. The seconds and minutes are constant, but our experience of them is mysterious, flowing according to rules we don't yet understand. Memory storage and retrieval. Your entire life, your first day of school, your happiest moments, your deepest regrets, is stored somewhere inside your brain. And yet how those memories are kept and how they return when you need them is still a mystery. Scientists know memories are not like files in a cabinet. They're patterns of activity across many neurons, spread across different regions. The hippocampus helps weave these patterns, acting as a kind of index. But exactly how the brain encodes a memory and later pulls it back is not fully understood. Sometimes memories change when we recall them, being reshaped before they're stored again. Sometimes we even create false memories that feel completely real. Why do some memories last a lifetime while others fade in days? Why does a certain smell suddenly unlock a vivid scene from childhood? Experiments show glimpses. Neurons that fire when a specific face is seen. Brain activity that mirrors memory recall. But the full picture is missing. Memory is the glue that makes us who we are. And yet the machinery behind it How moments become part of us and how they return years later is still unknown. Emotional origins. Emotions shape every part of life. Joy pushes us forward. Fear holds us back. Anger flares. Sadness weighs heavy. But where do they come from? Scientists know emotions involve the body as well as the brain. Your heart races when you're afraid. Your stomach knots when you're anxious. Tears well up when you're sad. But emotions' origins are still debated. Are they hardwired, ancient survival tools built into our biology? Or are they constructed by the brain, shaped by culture, memory, and interpretation? We know certain brain regions play a role. The amygdala for fear, the insula for disgust, the prefrontal cortex for regulation. But no single emotion center exists. Music can bring goosebumps. Scents can trigger sudden nostalgia. Sometimes we don't even know why we feel the way we do. Emotions are powerful guides, steering our choices often more than reason does. Yet the way they arise, the way they take hold of body and mind, remains one of the most intimate mysteries of being human. The source of creativity. An artist stares at a blank canvas, a writer at an empty page, a scientist at an unsolved problem. Hours may pass with nothing. And then suddenly, an idea arrives, clear, surprising, alive. Where did it come from? Creativity feels like a spark, but its origin is hidden. Some say it's the brain mixing and matching old ideas in new ways. Others think it requires stepping away, letting the subconscious work while the conscious mind rests. Many breakthroughs in history have come not at desks, but in dreams, showers, or quiet walks. Brain scans suggest different networks are involved, some generating ideas, others judging them. But this still doesn't explain the moment of inspiration. Why does the solution arrive suddenly with such force? Why do some people overflow with creative ideas while others struggle? Creativity is one of humanity's greatest gifts, shaping art, science, and progress. Yet the place where ideas come from, that quiet leap from nothing to something, is a mystery we still cannot explain. Déjà vu. You step into a room you've never been in before, and suddenly everything feels strangely familiar. You know what will happen next, though you don't. This is déjà vu, and it remains one of the mind's strangest mysteries. Scientists suggest it may be a trick of memory. Perhaps the brain misfires, creating a false signal of familiarity without a real memory behind it. Others think it happens when one part of the brain processes an experience slightly before another, making the moment feel like a repeat. Still others suggest it comes from similarities between a current scene and a forgotten past one, fooling the mind. What makes déjà vu so mysterious is its intensity. For a few seconds, reality feels doubled, both new and remembered. Almost everyone experiences it, yet no one can predict when or why. Déjà vu reminds us that memory and perception are fragile, and that the brain sometimes tricks us in ways we don't yet understand. The placebo effect. Imagine taking a pill, being told it will ease your pain, and then actually feeling better, even though the pill contained nothing at all. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain, ease depression, and even calm Parkinson's disease symptoms. The effect is thought to come from expectation, the belief that something will help triggers real changes in the brain and body. Placebos can release natural painkillers, alter brain chemistry, and affect the immune system. What makes the placebo so strange is that it can work even when people know they're taking one. Somehow, the ritual of treatment, the pill, the doctor, the belief, taps into hidden healing pathways. But why some people respond strongly to placebos and others do not is still unknown. The placebo effect blurs the line between mind and body, showing us that belief itself can sometimes heal in ways we still don't fully understand. Why we sleep every night, we surrender to sleep. We close our eyes, drift into dreams, and lose awareness for hours. But why do we need it? Sleep is dangerous if you think about it. In the wild, an animal that sleeps is vulnerable. Yet every species does it in some form. That suggests sleep is essential. But essential for what? Some scientists believe sleep helps the brain store memories and learn. Others think it clears away waste, cleaning the brain of harmful buildup. Sleep may restore energy, regulate emotions, and strengthen the immune system. It may even help the brain rewire itself, keeping connections balanced. And yet no single explanation fits all the evidence. Different animals sleep in very different ways. Dolphins sleep with only half their brain at a time. Some birds sleep while flying. Some creatures need very little sleep at all. What we know for sure is that without sleep, minds and bodies quickly break down. Why we spend a third of our lives doing it remains one of science's great mysteries. The aging process. Every living being on Earth ages. Skin wrinkles, hair turns grey, muscles weaken, and eventually the body begins to fail. But science cannot fully explain why aging happens or why it happens in such different ways across species. One explanation points to our DNA. Each time a cell divides, the protective caps at our chromosomes' ends, called telomeres, grow shorter. Eventually, the cell stops dividing altogether. Another theory blames damage. Oxygen molecules and other byproducts slowly corrode cells over time, leaving scars that accumulate. Others see aging as an evolution side effect, a trade-off that allows energy to be focused on reproduction in youth, but leaves the body vulnerable afterward. Yet nature presents exceptions. Some turtles and fish show almost no signs of aging. Certain jellyfish appear able to revert to earlier life stages, sidestepping decline altogether. Naked mole rats live far longer than expected, showing resilience against many age diseases. Why do some creatures resist aging while humans succumb to it? And why does the process unfold with such predictability in us? The answers remain elusive. Unlocking this mystery could change medicine forever. But for now, aging is a riddle written into our very cells. Surgery. Human lifespan limits. The longest confirmed human life ended at 122 years. But was this the upper ceiling of human biology, or just a remarkable outlier? The truth is no one knows. Some researchers argue humans have a hard limit. Beyond a certain age, the body cannot repair itself quickly enough to survive. Evidence suggests survival rates decline sharply after 110, hinting at a biological cap. Others insist there's no strict maximum, only ever-rising odds of frailty, disease, and chance. What's puzzling is that although average life expectancy has climbed dramatically thanks to medicine, hygiene, and nutrition, the maximum lifespan has barely budged. Almost no one lives past 115, no matter where or when. Still, scientists search for ways to extend life further. They study families of super-agers who remain healthy into extreme old age. They look for genes that resist disease and test drugs that slow aging in animals. Could humans someday reach 150 years or even 200? The data offers hints but no certainty. The upper boundary of human life remains hidden, waiting for someone to discover whether it's fixed or can be pushed further. Darpachiti. Animal regeneration. If a salamander loses a leg, it grows a new one. If a starfish loses an arm, it slowly rebuilds it. Even certain worms can regenerate an entire body from a single fragment. In nature, regeneration is surprisingly common, but humans cannot do it, except in the tiniest ways. A fingertip might regrow in a child, but a lost limb never returns. The question is, why them and not us? Scientists studying salamanders find that when they're injured, their cells near the wound seem to reset, rolling back into a flexible state like those of an embryo. From there, the cells grow into muscles, bones, and nerves, perfectly organized. Humans share many of the same genes. Yet for reasons we don't understand, our bodies do not use them in the same way. If we could unlock this ability, medicine would be transformed. Damaged hearts could heal themselves, spinal cords could regrow, limbs could return. And yet, despite decades of study, the full blueprint of regeneration remains hidden. Why nature allowed some creatures to wield this power while denying it to us is a mystery. For now, regeneration belongs to the salamander, the starfish, and a few others, a miracle we can only watch with awe. Exceptional longevity in nature. Most animals follow a simple pattern. Small bodies live short lives, large ones live longer. Mice live a few years. Elephants live many decades. Humans, with our long lives, are outliers among primates. But scattered across nature are creatures that defy these rules entirely. The Greenland shark glides beneath Arctic ice for centuries, its lifespan stretching more than 400 years. Bowhead whales sing in frozen seas for over 2 centuries. Tiny naked mole rats live 10 times longer than similar rodents, with remarkable resistance to age-related decline. Some clams have been discovered alive after more than 500 years. Why? Scientists have found clues: unusual proteins that resist damage, DNA repair systems that seem more efficient, metabolisms that move at an incredibly slow pace. But no single answer explains them all. Each species seems to have its own key to longevity, and humans cannot yet copy it. These creatures remind us that aging is not a fixed law of nature, but a puzzle with many solutions. If we could learn their secrets, we might one day unlock new ways to extend our own lives. For now, they remain timeless enigmas of the natural world. Surviving frozen, imagine being frozen into ice. Your blood crystallized, your heart silent, your body rigid. For most creatures, this means death, but not for all. The wood frog of North America freezes solid in winter. Its heart stops, its body stiffens. Yet when spring warmth returns, the frog thaws and hops away unharmed. Certain insects and fish can do the same. And tardigrades, tiny water bears, can endure extremes far beyond freezing, surviving in the vacuum of space itself. How do they do it? Some creatures fill their bodies with special antifreeze molecules that prevent ice crystals from shredding their cells. Others use sugars that stabilize tissues during freezing. But the exact details of how their brains, hearts, and other delicate organs survive months without activity remain unclear. If we could master this trick, it might change organ transplants, medicine, even space travel. We could preserve organs for months, maybe place humans into hibernation for long journeys. But for now, the secret belongs only to these hardy survivors, creatures that seem to laugh at the laws of life and death. Whale cancer resistance. The bowhead whale can live for more than 200 years, gliding through icy Arctic waters. What makes this astonishing is not just its age, but its health. Despite its massive size, with billions of cells and centuries of time for mutations, cancer is remarkably rare. This is known as Peto's paradox. Larger animals with more cells should, in theory, have higher cancer rates. But whales, elephants, and other giants don't. somehow they resist. In elephants, researchers have found extra copies of tumor suppressor genes, like extra layers of defense. In whales, the explanation is murkier. Perhaps their DNA repair systems are unusually strong. Perhaps their metabolism slows damage. Perhaps they have unique biological pathways we haven't discovered yet. If we could unlock this mystery, it might revolutionize cancer treatment for humans. Whales have cracked part of the code of long life without disease, but for now, their secret drifts beneath the waves, unsolved. Magnetic sense in birds. Every year, birds migrate across continents. Tiny warblers fly from Europe to Africa. Arctic terns cross oceans, circling the globe. They travel thousands of miles with uncanny accuracy. Part of their secret seems to lie in Earth's magnetic field, but how they sense it remains uncertain. Some evidence points to tiny crystals of magnetite in their bodies, acting as internal compasses. Other research suggests certain proteins in their eyes may let them see magnetic fields as faint patterns of light. But no single theory explains it all. What we know is that their ability is incredibly precise. Even on cloudy days when the sun and stars are hidden, birds stay on course. Released in unfamiliar lands, they still find their way. It's a sense humans lack, like an invisible layer of reality we cannot perceive. For birds, the world carries directions written into its very fabric, a compass we still don't understand. Monarch butterfly navigation. Every autumn, fragile monarch butterflies begin an impossible journey. They fly thousands of miles from the northern United States and Canada to a few mountain forests in central Mexico. There they gather in dense swarms, covering trees in shimmering orange. What makes this migration astounding is that no single butterfly completes the round trip. The ones that return north in spring are several generations removed from those that left in fall. Yet somehow they arrive at the very same groves year after year. Scientists know monarchs use the sun as a compass, adjusting for the time of day. They may also sense Earth's magnetic field. But how they pass this knowledge between generations, how a butterfly that has never made the journey knows exactly where to go, remains a mystery. It's one of the most breathtaking migrations on Earth, guided by a hidden map no human has ever read. Long-distance migration. The natural world is full of great migrations. Salmon hatch in mountain streams, swim to the sea, and years later return to the same stream to spawn. Sea turtles crawl from the ocean onto the very beach where they first hatched. Birds, whales, and insects all travel across the planet with astonishing accuracy. Scientists have discovered clues. Some animals use the stars, the sun, and Earth's axis tilt. Some may follow magnetic fields or subtle sense. Yet none of these explanations fully accounts for their precision. How does a bird find the same tree each year? How does a turtle cross an entire ocean to one patch of sand? These journeys remain partly unexplained, guided by senses we do not yet fully understand. Migration is one of life's oldest rhythms, a grand, mysterious dance written into animals' instincts. Homing pigeon navigation. For centuries, humans have marveled at homing pigeons. Release one hundreds of miles from home, and it will rise into the sky, circle, and then fly straight back to its loft. No map, no guide, just a hidden sense of direction. Researchers have proposed explanations. Some believe pigeons use the sun as a compass, adjusting for time. Others suggest they detect Earth's magnetic field, like a built-in GPS. Still others point to smell. The idea that pigeons build a scent map of their home region and follow it back. But none of these fully explain their uncanny accuracy. Even when released in strange places under cloudy skies, pigeons still find home. It's a mystery hidden in their biology, a secret compass we have yet to uncover. For pigeons, the world is filled with invisible cues that guide them across the sky. For us, it's still a puzzle unsolved. Human mysteries language is what makes us human. With it, we share ideas, pass down stories, and build civilizations. But how it began remains one of our past's greatest mysteries. Our closest relatives, chimpanzees and bonobos, can communicate with gestures and sounds, but none come close to human speech's complexity. At some point, our ancestors made the leap from simple calls to structured language, complete with grammar, abstraction, and infinite possibilities. But when and how did it happen? Some theories suggest language began as hand signals, with words coming later. Others propose that rhythmic sounds, chants, and songs gradually grew into spoken language. Archaeology shows us carvings and symbolic art tens of thousands of years old, suggesting the minds that created them were already capable of complex communication. But the sounds themselves left no trace. Language allows us to describe what is not present, to plan, to dream, to imagine. It's both a survival tool and a window into thought. Yet the first spark of language, the moment when humans first spoke, is lost in time. We can only guess at the conversations that began it all. Laughter's roots. Wherever you go in the world, people laugh. The sound crosses cultures, ages, and languages. Babies laugh long before they speak. Groups laugh together, their joy contagious. Yet why we laugh and how it first evolved remains uncertain. Some scientists believe laughter began as a signal of safety. Early humans may have laughed to show others that a threat had passed, turning fear into relief. Others trace it back to primates at play, whose panting sounds during wrestling and chasing resemble laughter's rhythm. But laughter is more than a survival tool. It lowers stress, bonds groups, and releases powerful chemicals that flood the body with calm. Strangely, we laugh not only at jokes, but also at relief, at awkwardness, even at sorrow. Sometimes laughter bursts out when it makes no sense at all. Why should a sound, a breathy burst of air, carry such power? We don't know. What we do know is that laughter is ancient, universal, and mysterious. It's the music of joy shared across all humanity, its roots still hidden in our past. Music's power. A melody can make us cry. A rhythm can make our hearts race. A song can bind us to memories we thought forgotten. Music has no obvious survival function, yet it shapes human life across every culture. Why? We don't know. Some suggest music evolved as a kind of glue, binding early communities through dance and song. Others think it began as courtship, a way to signal vitality and skill. Still others argue it's a byproduct of language and memory, a beautiful accident of evolution. What makes music even stranger is its power. Stroke patients who struggle to speak can still sing. People with dementia recall lyrics when almost everything else has faded. Music can synchronize heartbeats in groups, can calm newborns, can stir armies to march. Why should organized sound reach so deeply into our minds and bodies? Science has no clear answer. Music remains one of the most universal, mysterious forces in human life, an invisible thread that ties us together. Briseske Kurz, The Nature of Love. Love shapes human lives more than almost anything else. It binds parents to children, partners to one another, friends across time. It inspires art, sacrifice, and joy. Yet science still cannot fully explain what love is. Biology shows us pieces, Love floods the brain with dopamine and oxytocin, chemicals tied to reward and bonding. Evolutionary theory suggests it developed to keep parents together long enough to raise vulnerable offspring. But these explanations don't capture the full experience. Why does love sometimes arrive suddenly, overwhelming us? Why does it last a lifetime in some cases and fade in others? Why do people risk everything for it, even against reason? Love is not only chemistry or instinct, it's memory, story, imagination, and something more. We can map its effects in the brain, but not its meaning. Love is both universal and unique, an experience shared across humanity, yet different for every person. Its full nature remains one of the most profound mysteries of being alive. Emotional tears. Tears protect our eyes, washing away dust and salt. But only humans shed tears for reasons beyond biology, when we are sad, joyful, frustrated, or even overwhelmed with laughter. Why? One idea is that tears are a social signal, showing vulnerability and drawing empathy. Another suggests they release stress chemicals, though evidence is mixed. Tears may strengthen bonds, making emotions visible to others. What deepens the mystery is that we cry for opposite feelings. Tears come with grief and with joy, with sorrow and with relief. They fall silently in solitude or in the middle of laughter. No single explanation captures all of this. Tears remind us that we are emotional beings, not just logical ones. They make the invisible visible, carrying feelings from inside to the outside world. But the reason humans alone evolved this response remains unsolved. A secret hidden in every tear that falls. Recurring myths, from deserts to islands, mountains to forests, cultures separated by oceans, tell stories that echo one another. Myths of great floods, of sky gods, of tricksters, of underworlds. They appear again and again. Why? Some suggest human minds are wired for story, and certain themes arise naturally from shared experience. The fear of death, the hope for renewal, the awe of the sky. Others believe ancient myths spread through migration and trade, leaving echoes in distant lands. Still others wonder if myths are shaped by deeper patterns in the human brain, symbols born from the same inner landscape. Whatever the reason, myths carry truths that cultures find important. They explain the unexplainable, bind communities together, and pass wisdom through generations. But the strange recurrence of similar stories across the globe, appearing where no contact seems possible, remains a mystery. Cooperation with strangers humans are unusual among animals. We not only help family and close allies, but also strangers. We donate blood. We build communities. We risk ourselves for people we may never meet. Why? Evolutionary theories suggest cooperation evolved to strengthen groups, giving them an edge over rivals. Others point to reciprocal altruism, the idea that help given will one day be returned. But humans go beyond calculation. We volunteer, we share, we sacrifice, sometimes without any hope of reward. Experiments show even young children choose to help long before they fully understand rules or society. Something in us seems drawn toward cooperation, but its origins remain unclear. Did it arise from survival pressures or from something deeper? A moral instinct written into our minds. The willingness to help strangers remains one of humanity's most beautiful and most mysterious traits. The rise and fall of civilizations. Across history, mighty civilizations have grown, flourished, and then collapsed. The Maya, the Indus Valley, Mesopotamia, Rome, all rose to greatness only to fall. But why civilizations follow this arc remains debated. Some point to climate change, droughts and disasters. Others to war, corruption, or resource exhaustion. Still others believe civilizations carry within them patterns of growth and collapse, cycles that repeat regardless of time and place. The truth may be all of these, or something else entirely. What is striking is how sudden collapse can be. Great cities are abandoned, knowledge is lost, and generations vanish into silence. Civilization itself is fragile, and the forces that make it thrive or fail are not fully understood. We live within a vast and complex society, but history reminds us that nothing lasts forever, and the reasons why remain a mystery. Human curiosity. Why do we wonder? Why do we look up at the stars and ask questions no other creature seems to ask? Curiosity is one of humanity's defining traits, but where it comes from remains unclear. Some say curiosity is an extension of survival, helping us seek food, shelter, and safety. Others believe it grew as an evolutionary advantage, pushing us to explore, to invent, to imagine. But curiosity often goes far beyond survival. It drives us to study galaxies billions of light years away, to decode ancient languages, to ask questions with no practical answer at all. Children show curiosity from the very beginning, reaching for the unknown, asking endless questions. It seems built into us. But why this hunger for knowledge, why this restless drive to understand, is not yet explained. Curiosity pushes us forward, shaping science, art, and exploration. But its source, the spark behind the question why, is still one of life's mysteries. Storytelling's universality. Every culture tells stories, around fires, on stages, in books, in films. Humans shape words into narratives. Stories carry heroes and villains, struggles and triumphs. They entertain, they teach, they inspire. But why are they universal? Some suggest storytelling is a way to pass on knowledge, wrapping lessons in memory. Others think it binds communities, giving people shared myths and values. Some see it as practice, rehearsing challenges and choices safely in imagination. But stories often go beyond these roles. They create worlds that never existed, fill us with emotions for people who are not real, and linger in our minds for years. No other species does this. Why do humans need stories? Why do we long for them again and again? We don't know. What we do know is that storytelling is as ancient as language itself, a thread running through every culture, connecting us all. Strange natural phenomena. Most people know lightning as a flash in the sky, a jagged streak followed by thunder. But there's a far stranger phenomenon that has baffled observers for centuries: ball lightning. Instead of a quick bolt, it appears as a glowing sphere of light, floating silently, drifting across fields or even inside homes. Witnesses describe orbs the size of a grapefruit, glowing orange, white, or blue, sometimes lasting several seconds before vanishing or exploding with a pop. For centuries, ball lightning was dismissed as myth, a trick of the eyes. But in recent years, credible sightings and even a few scientific recordings suggest it's real. The problem is no one knows what it is. Some theories describe plasma trapped by electromagnetic fields. Others imagine vaporized silicon glowing after a strike. Some suggest chemical reactions sparked in the air. But no explanation fits every account. The mystery deepens because ball lightning has been seen indoors, even floating through windows without shattering them. It seems to ignore ordinary physics, behaving like both matter and light. Despite thousands of reports, it remains elusive, unpredictable, and unexplained. Ball lightning drifts through history as one of nature's strangest and most beautiful mysteries, a ghostly fire in the sky. Earthquake lights. During some powerful earthquakes, Witnesses report glowing lights in the sky. They take many forms: flickering blue flames along the ground, flashes like lightning above cities, or strange orbs floating over fault lines. These earthquake lights have been described for centuries, but modern cameras have also captured them, confirming they're real. What causes them remains unknown. One theory suggests that stressing rocks during an earthquake releases electrical charges, sparking light in the air. Another idea is that tectonic forces ionize gases near the ground, making them glow. But not every earthquake produces lights, and the appearances vary wildly. In some cases, the lights arrive before the earthquake, leading to speculation that they could act as a warning system. But their rarity and unpredictability make them difficult to study. Earthquake lights are among the most eerie natural mysteries, flashes of otherworldly glow in the midst of chaos, reminders that Earth itself may hold secrets written in fire and stone. Supereruption triggers, volcanoes, are among the most destructive forces on Earth. Most eruptions are dramatic but manageable: lava flows, ash plumes, small explosions. But every so often, a volcano erupts with unimaginable fury, blasting enough material into the sky to alter climate and spread devastation across continents. What makes some eruptions so catastrophic? Scientists know pressure builds as magma rises and gases expand, but the exact tipping point remains uncertain. Some volcanoes sit dormant for centuries, then erupt without warning. Others rumble and smoke for years but never explode. The mystery lies in what flips the balance from silence to disaster. Events like Krakatoa in 1883, Tambora in 1815, and Mount Toba's eruption 74,000 years ago unleashed energy on a scale rivaling nuclear weapons. Toba may even have nearly wiped out humanity. Yet modern science still cannot predict which volcanoes will erupt this way or when. We monitor tremors, measure gases, and scan magma chambers, but supereruptions' inner mechanics remain hidden. Volcanoes are reminders that Earth itself is alive and capable of mysteries we have yet to master. Saturn's ring north. Saturn's rings are among the solar system's most breathtaking sights. Vast bands of shimmering ice and dust encircling a giant planet. They stretch for hundreds of thousands of kilometers, yet are astonishingly thin, sometimes only a few dozen meters deep. For centuries, we assumed they were as old as Saturn itself, more than 4 billion years, but recent evidence suggests otherwise. The rings appear strangely clean, made mostly of bright ice with little dust. If they were ancient, they should be darker, dirtied by micrometeorite impacts over eons. Measurements from NASA's Cassini spacecraft hinted that the rings may be only a few 100 million years old, a blink of an eye in cosmic time. If true, how did they form so recently? Perhaps a moon wandered too close and was torn apart by Saturn's gravity. Perhaps comets or asteroids shattered, leaving debris that spread into rings. But no explanation is certain. Saturn's rings may be temporary, destined to fall into the planet over the next 100 million years. We're living in the brief era when Saturn wears this dazzling crown. The mystery of their origin remains one of the solar system's most beautiful unsolved puzzles. Uranus's tilt. Among the planets, Uranus is bizarre. Instead of spinning upright like Earth, it rolls through space on its side. Its axis is tilted by 98 degrees, leaving it rotating almost horizontally. For part of its orbit, one pole points directly at the Sun, bathing that hemisphere in decades of sunlight, while the other lies in darkness. How did Uranus end up this way? The leading idea is that long ago, A colossal impact with a protoplanet knocked it onto its side. But such a collision should have left behind signs, like a large moon or a scar in its atmosphere. Another theory suggests multiple smaller impacts slowly tilted the planet. Still, others propose that gravitational interactions with giant planets in the early solar system pulled Uranus into its strange posture. Whatever the cause, Uranus remains unique. Its sideways spin creates bizarre seasons and may even influence its magnetic field, which is also oddly tilted and offset. No probe has visited Uranus since Voyager 2 in the 1980s, leaving most of its mysteries unsolved. Until we return, Uranus rolls quietly on its side, carrying a cosmic riddle no other planet shares. Venus's backward rotation, Venus, often called Earth's twin, is nearly the same size and mass as our planet, but it's also profoundly strange. One of its oddest features is its rotation. While most planets spin in the same direction they orbit the Sun, Venus rotates the other way. On Venus, the Sun rises in the west and sets in the east. Even stranger, a single day on Venus lasts longer than its year. How did this happen? One idea is that Venus was struck by a massive object early in its history, flipping its spin. Another suggests tidal interactions with the Sun slowly reversed its rotation. Still, another theory imagines Venus once spun rapidly like Earth, but its thick atmosphere and internal dynamics gradually slowed and reversed it. No theory fully explains the planet we see today. Its atmosphere, dense with carbon dioxide and sulfuric acid, may hold clues, but for now, Venus keeps her secrets. Beneath her perpetual clouds, Venus turns slowly backward and against expectation, a reminder that even familiar-looking worlds can hide the strangest histories. Neptune's storms at the solar system's edge. Neptune howls with winds faster than any on Earth, reaching nearly 2,000 kilometers/h. Vast storms swirl across its deep blue atmosphere, appearing and vanishing in ways that baffle scientists. The most famous, the Great Dark Spot, was discovered by Voyager 2 in 1989, a storm the size of Earth. But when Hubble Space Telescope looked a few years later, it had disappeared completely. Other dark spots have since appeared, shifting across the planet, sometimes breaking apart or fading without warning. Why does Neptune, so far from the Sun, have such violent weather? Its distance means it receives little solar energy. Some believe Neptune's internal heat drives the storms. Others think dynamics in its atmosphere amplify small changes into massive tempests. But the details remain unclear. Neptune remains a distant storm world, visited by only one spacecraft. Its mysterious weather shows us that even in the solar system's frozen reaches, chaos can reign. Jupiter's Great Red Spot. For as long as humans have pointed telescopes at Jupiter, the Great Red Spot has swirled in its atmosphere. A storm so large it could swallow Earth whole. It's been raging for at least 350 years, perhaps much longer. But why it began and why it has lasted so long remain mysteries. The storm is an anticyclone, spinning counterclockwise in Jupiter's southern hemisphere. Powered by the planet's immense atmosphere, it seems almost eternal. Yet in recent decades, scientists have noticed it's shrinking. Once wide enough to fit 3 Earths across, it now spans barely more than 1. Some predict it may fade away entirely in the coming century. Why did the storm form where it did? Why has it lasted centuries when storms on Earth last only days or weeks? And will it truly vanish or revive itself in cycles we don't yet understand? The Great Red Spot is a cosmic paradox, at once ancient and fragile. It remains one of the most iconic mysteries in the skies. The Oort cloud comets, with their glowing tails, have fascinated humans for millennia. They swoop in from the solar system's edges, loop around the sun, and vanish again into the dark. Astronomers believe these icy wanderers come from a vast reservoir far beyond Pluto, the Oort cloud. The Oort cloud is thought to contain trillions of icy bodies, leftovers from the solar system's birth. It stretches so far that its edge may blend into interstellar space. And yet, despite being comet's source, it has never been observed directly. The objects are too small, too distant, and too faint. We know the Oort cloud only from the comets it sends us, visitors that hint at the vast unseen population beyond. Was it formed by early planet scattering? Does it extend farther than we imagine? We don't know. The Oort cloud is the great unseen frontier of our solar system, a ghostly shell surrounding us, full of secrets we have yet to glimpse. Subsurface oceans. Beyond Earth, water is not rare. Moons like Europa, Enceladus, and Titan all hide oceans beneath shells of ice. Some of these oceans may be larger than all the seas on Earth combined. They're kept liquid by their planet's gravitational pull, which kneads the moon's interiors and generates heat. What makes these oceans exciting is their potential for life. On Earth, where water exists, life almost always follows. Hydrothermal vents deep in our seas thrive with creatures independent of sunlight. Could similar ecosystems exist beneath alien ice? We have hints. Enceladus sprays plumes of water into space, rich with organic molecules. Europa's cracked surface shows signs of activity below, but we cannot yet see into these oceans directly. What strange forms of life might swim there? Simple microbes, or something far more complex? Until we explore these hidden seas, the answer remains locked beneath ice, waiting in the dark. Enceladus's plumes, Saturn's small moon. Enceladus looks unassuming, just a bright, icy sphere. But when NASA's Cassini spacecraft flew past, it discovered geysers erupting from cracks near the South Pole, spraying water vapor and ice grains far into space. These plumes contain salts, organics, and even signs of chemical reactions that on Earth would hint at habitability. Beneath the surface, Enceladus hides a global ocean, kept warm by Saturn's tidal pull. The geysers may be vents connecting this ocean to the surface. But what drives the eruptions? Are they powered by hydrothermal vents at the seafloor, like those on Earth's oceans that teem with life? Or are they fueled by some other unknown process? Enceladus is small, barely 500 kilometers across, yet it has become one of the most promising places to search for life beyond Earth. Its plumes offer a direct sample of its hidden sea. But until we return with new missions, the mystery of what stirs beneath its ice remains unsolved. The Shurish, Titan's methane cycle. Titan, Saturn's largest moon, is a world both familiar and alien. It has lakes and seas, rivers and rain, but instead of water, they're made of liquid methane and ethane. Titan's skies are hazy, its surface sculpted by weather utterly unlike Earth's. Here's the mystery. Methane in Titan's atmosphere should be destroyed by sunlight over time. If that were the case, the methane seas would have long since vanished. Yet they're still there. Something, deep underground or hidden within Titan's chemistry, keeps replenishing them. Some suggest cryovolcanoes may release methane from Titan's interior. Others imagine chemical processes we don't yet understand. Intriguingly, some researchers note that methane is also a potential biosignature, a sign of life. Could Titan's methane be biological in origin? We don't know. Titan's methane cycle mirrors Earth's water cycle in eerie ways. But the source that sustains it, the hidden pump that keeps its seas full, remains a mystery waiting to be solved. Mars's lost water. Billions of years ago, Mars was a very different world. Vast river valleys carved the surface. Deltas and lake beds mark where water once pooled. The planet may even have had oceans. Today, it's dry and frozen, with only thin wisps of water vapor in the air. What happened to all that water? Some may be locked as ice beneath the surface. Some may be trapped in minerals. Much of it may have escaped into space when Mars lost its protective magnetic field. But the full story is unclear. Mars is littered with evidence of its watery past, yet its present is a desert. Did the water disappear slowly, or in sudden shifts? Could liquid water still flow underground today, hidden from our view? The fate of Mars's rivers remains one of the greatest planetary mysteries. To solve it may be to understand whether the planet once supported life, and whether it still could. Mathematical perfection. Mathematics is a language of patterns, a human invention built from numbers, symbols, and logic. Yet astonishingly, it describes the universe with almost perfect precision. Equations dreamed up on paper turn out to govern stars, atoms, and galaxies. Einstein's equations predicted black holes before anyone had seen one. Maxwell's formulas described radio waves long before they were detected. Why should abstract symbols map so exactly onto reality? Some scientists argue that math is discovered, not invented, that it reveals truths built into the cosmos's structure. Others suggest math is a tool shaped by human minds, tuned by evolution to fit the patterns we see. But neither answer explains mathematics' eerie accuracy in physics. Why should the same formulas describe both a thrown ball's arc and distant planet's motion? Mathematics is at once a human creation and a universal key. Why it works so uncannily well remains one of existence's deepest mysteries. Nature's constants. Every law of physics rests on constants: the speed of light, the electron's charge, gravity's strength. These numbers define how the universe works. Change them slightly, and stars might never form, chemistry might not exist, life might be impossible. But why do they have the values they do? Scientists measure these constants with exquisite precision, but no theory explains why they are what they are. Some suggest they're simply accidents of the universe. Others imagine a multiverse where countless universes exist, each with different values, and we just happen to live in one where life is possible. But these remain speculations. The constants of nature are like settings on a cosmic dial, fixed, precise, and unexplained. They're the background music of the universe, a melody we can hear but not compose. True randomness. Flip a coin, roll dice, shuffle cards. Randomness seems obvious. Yet physics makes the question stranger. At the quantum level, particles behave unpredictably. An electron may appear here or there. A radioactive atom may decay now or later, with no cause we can see. Is this true randomness, or just complexity beyond our understanding? Einstein famously resisted the idea, saying, "God does not play dice with the universe." He believed hidden laws must govern quantum events. But decades of experiments suggest otherwise. Quantum mechanics really may be irreducibly random. Still, some scientists believe deeper rules are waiting to be discovered. Others think randomness is woven into reality's fabric. If true randomness exists, then uncertainty is not just ignorance, it's part of what reality is. Whether the universe is fundamentally ordered or truly random remains an unanswered question at physics' heart. Time's nature. We live in time. We feel it flow second by second, carrying us from past to future. Yet science cannot fully explain what time is. Einstein showed that time is not absolute. It bends and stretches depending on speed and gravity. A clock on a mountain ticks faster than one at sea level. A clock in orbit ticks differently than one on Earth. Time is woven with space into a single fabric. But why do we experience it as a one-way arrow? Why does the past feel fixed while the future remains open? Some physicists think time's arrow is tied to entropy, disorder's tendency to increase. But this only pushes the question back. Why was the universe born in such an ordered state? Others suggest time itself might be an illusion, a trick of human perception. Time governs every heartbeat, every thought, every life. Yet its true nature remains one of the most profound mysteries we face. Matter-antimatter asymmetry. When the universe began, the Big Bang should have created equal amounts of matter and antimatter. But when matter and antimatter meet, they annihilate into pure energy. If they had been perfectly balanced, everything should have disappeared in a flash, leaving no stars, no planets, no people. And yet, here we are. Somehow, matter won. Why did matter gain the upper hand? Experiments show matter and antimatter behave almost identically, with tiny asymmetries. These slight differences may have tilted the balance in the early universe, but they don't seem large enough to explain why anything exists at all. Somewhere in the early cosmos's physics lies the reason why there is something instead of nothing. Until we find it, matter's victory over antimatter remains an unsolved riddle. The Higgs mystery: everything around us has mass, from stars to sand to our own bodies. But what gives particles mass at all? For decades, this was one of physics' biggest mysteries. The discovery of the Higgs boson in 2012 confirmed that an invisible field pervades the universe. As particles move through it, they acquire mass, like swimmers pushing against water. Without this field, matter as we know it could not exist. But the Higgs mechanism answers only part of the question. Why does the Higgs field itself exist? Why does it have the strength it does? And why do different particles interact with it so differently? The Higgs discovery opened the door, but behind it lies a deeper mystery. Mass feels solid and obvious, but its origins remain partly hidden in the cosmos' invisible fields. Reality's texture. To our eyes, reality feels smooth. Space seems infinitely divisible, like a line you can cut forever. But at the smaller scales, physics may be different. Some theories suggest the universe is pixelated, made of tiny, indivisible units, like pixels on a screen. This smallest length, the Planck scale, is far beyond what we can observe, but it might be everything's foundation. If reality is pixelated, then space and time themselves are not smooth but granular. Physics rules would need rewriting, but so far, no experiment has confirmed this. Whether the universe is continuous or digital remains one of science's strangest questions. The answer could reveal reality's true texture itself. The smallest length physics pushes us to ever smaller scales. Atoms, once thought indivisible, were split into protons and electrons. Protons themselves turned out to be made of quarks. Yet at some point, there may be a smallest length, a limit beyond which smaller has no meaning. This is thought to be the Planck length, unimaginably tiny, about 10⁻⁵ meters. At this scale, space may no longer be smooth but foamy and uncertain, a quantum haze, but no experiment can reach it yet. If space has a smallest unit, then the universe is not infinitely divisible. Reality would have a bottom floor, the smallest brick of existence. Whether such a limit exists remains one of physics' deepest mysteries. Why these laws? The universe runs on laws: gravity, electromagnetism, quantum mechanics. They're elegant, precise, and consistent, but they could have been otherwise. Why this set of laws and not another? Why a universe where stars can form instead of one where matter collapses or drifts apart? Some scientists imagine countless universes, each with different laws, and ours is simply one where conditions allow life. Others think deeper principles, still unknown, fix the laws in place. But for now, the law's origin themselves remains unexplained. We can describe the rules. We cannot yet explain why these rules and not others are written into reality. The greatest mystery science has carried us far. We've mapped galaxies, split atoms, decoded DNA, and walked on the moon. Each answer reveals more questions. Each discovery opens new mysteries. Perhaps one day we will explain consciousness, life's origin, the universe's birth, time's nature itself. Or perhaps there will always be questions just beyond our reach, mysteries woven into existence's fabric. The greatest mystery may not be the universe itself, but our place within it, whether human minds can ever truly comprehend reality's totality. As you drift to sleep, you might hold that thought gently. That curiosity itself is part of the mystery. To wonder is to be human, and to seek is to be alive. The questions may never end, but neither will our search. You've just traveled through 100 of science's greatest mysteries, questions that stretch from the cells in our bodies to the universe's edges themselves. Each one is a reminder that for all we've discovered, the world remains far deeper, stranger, and more beautiful than we can fully grasp. Think of what we've touched tonight, the hidden spark of consciousness, the riddles of aging and memory, the secrets carried by oceans beneath icy moons, the timeless puzzles of stars, storms, and reality's fabric itself. Some of these questions may be answered in your lifetime. Others may remain mysteries for generations, and still others may never be solved at all. But that is part of the wonder. To live in a universe that still holds so much unknown is to live in a universe filled with possibility. Every unanswered question is an open door. Every mystery an invitation. The fact that we don't yet know keeps science alive, keeps curiosity burning, and keeps us leaning forward into tomorrow. And as you lie here now, letting the weight of these mysteries drift across your mind, notice how gently they pull you toward rest. Like the slow rhythm of waves on a shore, the questions themselves are soothing. They don't need answers tonight. They only need to be carried, like starlight across a dark sky, questions above, questions below, a galaxy of wonder all around you. And you at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace. So let your breathing fall into rhythm. Let your body grow heavy and your thoughts soften. Imagine yourself floating through the mysteries we've explored, passing by them as if through constellations in the night. Questions above, questions below, a galaxy of wonder all around you. And you at the quiet center, resting in the knowledge that mystery itself is a kind of lullaby, one that will carry you into sleep. Good night, and may your dreams be filled with wonder.